So here in lecture 3.2, we're going to continue working on computational Boolean algebra, and we're going to continue our development of the binary decision diagram BDDs. In the last lecture, we showed that a decision diagram was a way of representing something like a truth table, but just way too big. And one of the first things that we did was to decide that we should order the variables in an attempt to make the diagrams all the same for a given piece of Boolean logic. We're going to continue constraining and restricting the decision diagrams. We're going to introduce another big idea in this lecture, which is that we're going to reduce the diagrams. We're going to remove certain forms of redundancy from the diagrams so that we have a really wonderful property, which is that if you give me a Boolean equation and you constrain the order in which the variables appear in the BDD, I always get the same diagram. I always get the same graph. It turns out that by making the data structure canonical in this way, it becomes an amazingly powerful tool for actually manipulating Boolean objects and answering really interesting questions. So let's see how that works.
We are back again looking at binary decision diagrams, and our first two big ideas, just by way of review, were the first idea was, hey, let's use a decision diagram. And the second big idea was, hey, let's impose a global variable ordering so that every path from the root to the leaf visits the variables in the same order. And what we got was the fact that the BDDs we create are still not canonical. We can have two different BDDs representing the same function. So I need another big idea. And this is the next really important idea, the idea of reduction. This is the idea that, there are redundancies in the graph that can remove unnecessary nodes and edges. There are things that are not needed. We can get rid of some nodes, we can get rid of some edges, and we can, if you will, tighten up the graph, make it smaller. So at the end of the previous lecture, we took the x2 node out and its children and we replaced it. That was an example of this. Why are we doing this? Well, we're doing this for two extremely useful reasons. The first is graph size. I would like the resulting data structure to be as small as possible. Well, that makes sense, right? Why use more computer memory if I don't need it? But the second is that I really want a canonical form. For the same Boolean function, if you give me the same variable order, I want there to be exactly one graph that represents this function. And that's going to turn out to be a tremendously powerful idea if we can make that happen. So we're going to use some reduction rules. And a reduction rule just identifies things in a decision diagram that are inefficient, that can be replaced with fewer nodes or fewer edges. So the first reduction rule is really simple, and it says we should just keep one copy of each constant leaf. And so that's the rule that says merge equivalent leaf nodes. And all that really says is I really only need one 0 node at the bottom of this binary decision diagram, and I only need one 1 node at the bottom of this decision diagram, and I could really get rid of all these other separate copies, and I could just take all of those edges in the very large initial diagram, and I could redirect whatever variable node has an edge into the constant node. I could redirect that into a single copy of the 0 and a single copy of the 1. And if we were to take all of those edges that come out of the 4x3 nodes at the bottom of the unreduced version of the binary decision diagram, and simply redirect them into a single 0 node and a single 1 node, that's what we get. And so, oh look, that's a lot better. Like I said, you have a function of 100 variables, you have 2 to the 100 of these things down at the bottom. Now you've got 2. That's good. But, we can still do a whole lot better because, the stuff up at the top, as I'm circling here with this triangle of the top part of the BDD, well, there's still 1x1 node, 2x2 nodes, and 4x3 nodes, in that triangle. I haven't really made things any better, but at least for the constant nodes, this is just less silly. This is less inefficient. This makes much sense. But let's look at a more interesting reduction rule, something that really, in a more powerful way, reduces the insides of these decision diagrams. So here's the second reduction rule, and this has a more interesting name. It says merge isomorphic nodes. Okay, what is an isomorphic node? An isomorphic node are two names that have two important characteristics. They are the same variable and they have identical children. Now the same variable, that's kind of an easy one. You're never going to merge an x and a y or an x and a q. Okay? You can merge an x and an x. But identical children means that they are exactly the same physical children. They are not just children with the same label. And so we have an example up here of isomorphic nodes. The x nodes are isomorphic. Right now, the x nodes have the same variable. Okay, they are both x nodes. And the x nodes also have identical children. And by that I mean their low pointers, which point to their 0 children, both go to a y node. And their high pointers, which go, when the value is set to a 1, both go to the z node. And they don't go to any old y, random y node or z node. They both go to the same x, y node and the same z node, the exact same nodes. And so what happens up here is that I don't need both of them. I can get rid of one of them. And so I can simply replace it with one, any one, it doesn't matter. And I can keep the children, right, as I'm just drawing here, right? So there's an x node, its low child goes to y, and its high child goes to z, and then y and z are unaffected. But there are two pointers that go into, in this case, two pointers that go into the x nodes. One of them goes into the left x node, and one of them goes into the right x node. And what now happens is that you simply redirect them both to go into the x node. So whatever was happening above the x node in this BDD, right, and that traversed some edge with a variable decision to get to x, those pointers, they just point to the single copy of x. And there's a little gray box over at the side here that just gives the recipe. You remove the redundant node, which in this case is the extra x node. You redirect all the edges that went into the redundant node into the one copy that you kept. And so in this case, the edges into the right x node are now going into the left x node as well. That is an example of merging isomorphic nodes to reduce the complexity of the BDD. So let us apply Rule 2 to our example. And if we stare at it for a little while, the big thing that we have to look for is what are some nodes that have the same variable, label, and identical children. So there's just no other node than x1, so it can't be x1. And if we look at the x2s, they don't have identical children. But if we stare at the x3s for a little while, what we will discover is that those folks, the rightmost x3s, those are all isomorphic. They all have 0 as the low child and 1 as the high child. And so I only need one of them. I don't need all of them. So I can redraw this BDD. It's got an x1, okay, at the top, and then it's got, at the next rank, it's got two x2 nodes, right, and the low child goes to the left x2 node and the high child goes to the right x2 node. And then on the right side, there is a single x3 child, right, and there is the high child of x2 and the low child of x2 both go to that single x3 node. I'm going to put little stars by them because those are new edges. On the left-hand side, the x2 node also goes, its low child goes to the x3 node. And down at the bottom, I have a single 0 constant and a single 1 constant. The x3 child on the left, both of its children, low and high, go to the 0 node. The x3 node on the right, the low child goes to the 0 node, but the high child goes to the 1 node. And the x2 node on the left, right, that high child goes to x3. And I'm going to put a little star by that. All right. So those are all of the things that I redid, right, as a consequence of killing 2 of the 3 x3 nodes and replacing them with a single x3 node. And one of the things you can immediately see is that there's less to this graph. There's just less of it. It's a lot less complicated. That's a good thing. Simpler's got to be better. But wait, there's more. There's another rule that we can use to eliminate redundant nodes. And this is the rule called eliminate redundant tests. And this is another one of the ones that feels kind of simple when you look at it. A test in this case means a variable node, right? So this is, if x equals 1, what do I do? If x equals 0, what do I do? Redundant tests are the circumstance where a variable has both of its children going to the same node. And that's just dumb, right? I don't need, in the diagram above, I don't need to know what x is. If x is 0, I go ask the y node what to do. If x is 1, I go ask the y node what to do. That's not necessary, right? And so I can kill the x node. I can keep the y node, right? And again, when I look at in this case, the edges that were going into the x node, however many of them there are, I simply redirect them to go into the y node instead. I bypass the x node. The x node goes away. I do not care what value it takes. It does not affect the output of my function, and so I get rid of it. And so, again, there is a little gray box at the upper right that gives you a little formula. It says remove the redundant node, redirect all edges into the redundant node, which was x in this case, into the child y in this case of the removed node. So that's the recipe, but it simplifies things. So if we go back to our evolving BDD, and we apply Rule 3, what I have drawn on the left was the same example that I did by hand a couple of slides ago. X1 is the top rank node. It has low children and high child X2 respectively, right? The next rank are two X3s, right? The X2 on the left has a low child that goes to X3. The high child is the right X3. The X2 on the right, both of the children go to the right X3. The X3 on the left, both of them go to 0, and the X3 on the right, low goes to 0, high goes to 1. We can immediately look at this and we can see that the X3 on the left is redundant because both of its children go to the 0 node. And the X2 on the right is redundant because both of its children go to the X3 node, and so I can kill both of them. I can just kill them both, and I can redirect the edges. I'm going to put little stars by them. I can redirect the edges that go into those nodes that I kill. I can simply send them to their children, right? And so in the right-hand diagram, I'm going to put a little star by each of the edges that were redirected, and we have a vastly simpler BDD. There's an X1 node at the top, and there's a single X2 node at the second rank. X1's low child is this X2 node. There's a single X3 node at the third rank. X1's high child is that X3 node. X2's high child is that X3 node. And then there are constants at the bottom. X2's low child is the 0. X3's low child is the 0. X3's high child is the 1. Wow, this is way less BDD than I started with. This is way less graph than I started this. This is way fewer nodes and way fewer edges. Now, you might ask, how does one apply these rules? And for now, I'm just going to say iteratively. When you can't find another graph match, the graph is reduced. Is this how programs really do it? No, absolutely not. Not only no, no with 2 exclamation points. Look, if I give you a function with 100 variables, the way I just showed you, you have to build the decision diagram with 2 to the 100, nodes at the bottom, and then you have to apply this reduction stuff. That's crazy. There's no way you could do that. There's actually a much smarter set of ways, and we'll do a very high-level overview of what those ways are. But for now, and for some homework problems, and for just sort of getting kind of intellectually on top of this stuff, if I give you a function with 3 or 4 variables and I ask you to do the BDD, it's perfectly okay to just do this by hand. You'll get the right answer and you'll get some insight into how this stuff works. Now, the big thing going on here is that we started with a decision diagram, and it was really big. And we ordered the variables and we said, let's see if that makes the graph that we get canonical, if we always get the same graph. And the answer was no, because there can be redundancies. Even if you always visit all the variables in the same order from the root to the leaf as you do decisions, you can still get a different graph. And so then we reduced the diagram by all of these merging operations. And we got a new thing. We got a thing called a reduced ordered BDD. And the result of that is a really, really cool result. And the really cool result is that A reduced ordered BDD is a canonical form, right? So I'm just going to say data structure for any Boolean function. I'm going to stop it with an exclamation point. A reduced ordered BDD is a canonical form. The same function always generates exactly the same graph, exactly the same nodes with exactly the same edges, with exactly the same children, if you give me the same variable ordering. Two Boolean functions are identical if and only if their reduced ordered BDD graphs are isomorphic, which is a fancy way of saying they are the same. Now, you might think, wow, how hard is that to check? And the answer is going to be, amazingly, trivial. It's a wonderful result. And this is a really beautiful property to have, that the simplest form of the graph, the most efficient form of the graph, the form of the graph that uses the least amount of computer resources, is the canonical form. That's just a lovely, lovely sort of unexpected consequence of the whole BDD development. So this is the reduced ordered BDD. You know, we've shown sort of how to build it. What we want to do next is start talking about more of the properties for you know how we do these things in the real world.